Alright guys, it's Mark Elkin here, Hidden Knowledge, unravelling the pole shift. Now, I just wanted to run over some graphs and charts and stuff like that, just so that you guys can get a better understanding of what you're looking at when you're looking at it. I know Laura Wells has done a YouTube video and referred to my Patreon posts, and she's done a great job of explaining it. But I know a few people haven't seen that video, so I thought I'd do a quick one and just give you a bit more insight of what you're looking at. Just so you get a better idea, because obviously on my Patreon posts, I'm writing a lot of text as well as looking at the images. It's quite a lot to take in, I know that. So hopefully this will just help you out a bit, okay? So what I'll do is I'll try and get in. I would have used my computer, but it's so slow and it keeps messing up. I need to get a new one. But hopefully this loads up pretty quick. So we're just going to look at the solar wind first. I'm not sure how this picture's going to come out on my phone, but hey, we've got to try. Okay, so hopefully you can see my cursor, which is here. So what we're looking at here is obviously the sun, self-explanatory. And what comes from the sun is this solar wind, you see? You see these lines here? This is classed as a solar wind. Primarily electrons, protons and alpha particles, which are highly electrically charged. So what happens is, it comes in and it hits our bow shock. This is classed as our bow shock here. So if you follow my cursor, this is our bow shock, okay? This here, that's our magnetosphere. If you follow the cursor, that's our magnetosphere, and it comes out the back as well. I mean, this surrounds the planet. This is just this is just an illustration of what it looks like side view. But these field lines would literally do 360 right around the planet, okay? So what happens is, electrons, protons, alpha particles come in, they hit our magnetosphere here, and this compresses our magnetosphere. Sorry, it hits our magnetoshield, which is classed as our bow shock, okay? It's like a force field. It just stops all the charged particles getting through, directly hitting Earth. Sometimes they do, depends on the compression. If it's severe, then it will break through there. Okay, so what it does, it hits here, compresses these magnetic field lines here, our magnetosphere, and then it gets pulled in at the poles, the particles, okay? Pulled in at the poles, and that's what gives us our northern and southern green auroras, okay? So the stronger this compression is, the brighter the auroras are here and here, okay? If we look at the back, this is our magnetopause here. Okay, that's our magnetopause, this bit here. And at the back is our magnetotail, but you can't really see it in this image, so I'll get another one up. Okay, where are we looking at? Okay, this is, let's look at this one, because we do a lot of these, we post a lot of these. So if I just explain to you what these actually mean. So this is actually from a NOAA website. So this is classed as a normal magnetopause, okay? So this is like reversed to what I just showed you. So the bow shock is this way now, look, you see? Imagine the camera's on the other side of the planet looking at it from the opposite way. So that's our magnetosphere. This yellow hue here, that's our magnetosphere, okay? If I zoom in a little bit more. This bit here, these red ones here, these red lines, that's our magnetosphere, okay? Like again, it goes all the way around the planet, comes out the back. This red hue that you see here, that's our plasmasphere, okay? That's our plasmasphere. The bit in the centre, this white and black dot, that's Earth, okay? So the white side is the day side, the black side is the night time. These lines here, coming out here, top and bottom, that's our magnetic field lines, okay? This bit here is our magnetopause, the outermost layer, this bit here, magnetopause, and this is our magnetotail. This whole section here is our magnetotail, okay? Right, this is what they class as normal, which it is. You know, there's hardly any compression on the bow shock. The magnetosphere seems okay, structured well. Now this is what NASA and NOAA class as severely compressed, okay? So just take note of what this looks like. And they say this is severely compressed, okay? So you look at our bow shock now, it's gone a different colour. It's gone a bit darker, like a shade of green instead of yellow. So it's under like a slight compression. Even though they say it's a severe compression, mind you, this is actually a very slight compression. This is nothing compared to what we're used to now. But as you can see, these magnetic field lines get a bit closer together. Our magnetosphere compresses slightly. It gets a bit yellow around the whole globe and whole magnetosphere. Do you see what I mean? And then the magnetopause and magnetotail gets disrupted because the particles are coming in, because they're electromagnetic, and our magnetic field lines are magnetic, of course. It just interferes with the magnetosphere and the magnetotail and everything, okay? So that's what they class as severely compressed. Now, this is actually what we're used to now. This is the new normal for Earth, okay? So you imagine our bow shock, look, in the previous one, it was just yellow, okay? And now look in front of Earth, that's all yellow, so that's all charged. That's like cosmic radiation continuously in front of Earth's bow shock, okay? So the bow shock is struggling to keep up now. Do you see? Look, it's just superheated. That red, that's our bow shock. And it is under severe heat all the time, okay? And you can see our magnetosphere is struggling as well. Look, it's all yellow in our magnetosphere, do you see? Okay? And at the back, look, you see all these red eddy formations? It's because there's particles coming up from under the ecliptic. So this is the sun. Excuse my brilliant artwork that I've done here. It's great, isn't it? This is our sun. So imagine our sun's here. All the solar wind is coming from here, look, from the sun, hitting our bow shot. Okay? And then, look, it's that the actual new particles, or the southern particles, are coming from here, under the ecliptic, and hitting our magnetopause here. This is what happens. It comes in, and then they get pulled in and whipped out, you see? And then, again, because they're electromagnetic particles, it interferes with the magnetics of our magnetotail. And that's why eddy formations form. Because as soon as they hit the magnetosphere and magnetotail, it just disrupts all the magnetics. So you get little eddy formations. This happens as well when the moon is behind Earth. Okay? That's what happens when the moon is... When we get a full moon, it means it's behind Earth, okay? So that can cause eddy formations too, because the particles can literally bounce off the magnetics of the moon and directly go back to Earth, into the tail, and cause eddy formations again, okay? So just so you get a better understanding of what we're talking about, like eddy formations and our bow shock, our magnetosphere, our magnetotail, our magnetopause. You know, I just wanted to go over bits like that because I know a lot of people struggle with these graphs and that, okay? Right, let's look at something else. Excuse me. Okay, so ionospheric charging. So imagine them particles from the solar wind is coming in, hitting our magnetosphere, well, hitting our magnetopause, our magnetosphere, our bow shock, and then they get pulled in at the poles and they spread throughout the ionosphere. Ionisation process takes place. Okay, and this is where you get superheated ionosphere, but ionospheric charging. Okay, when it's white, ignore the date, by the way, because this is a few days old, but I had to gather all the information and data just so I could do this video, really. So it's just so you can get a better understanding of what you're looking at, okay? So this red and white is under extreme heat, okay? And the blue is under extreme charge. See this? Now this correlates to where earthquakes occur as well because of the rock formation. I've done a post on Patreon about that too, which I'll post in the links below. So yeah, this is what happens when they get pulled into the poles and spread through the ionosphere. I mean, HAARP has a big, you know, they play a big part in it, but it's not always HAARP. It's not always CERN, it's not always Gwen, it's not always base systems, it's not always NextRad. And if you don't know what I'm on about when you're talking here, refer to my CERN post, which will be on Facebook. Just search my name, search the CERN post, and it should pop up. And it explains all the Gwen towers, the HAARP, and you know, stuff like that. Okay, so that's the ionospheric charging. Now, okay, just so you get an understanding of when it hits our magnetopause or magnetotail, whatever, as soon as it gets pulled in at the poles, this is what occurs, okay? So the charged particles get pulled in at the poles magnetically. And you see these, let me go a bit closer. You see these lines here? See these lines? There are horizontal magnetic field lines, okay? This has a lot to do with the KP index, which I'll get to in a second, just so you get a better understanding of that too, okay? So this is classed as a KP9, which is the most severe geomagnetic storm you can get. This only goes up to number 9, So when we get severe compression on our bow shock and our magnetosphere, this is what occurs. So the green auroras will be seen a lot more south from the north. Okay, so that's nearly touching. I mean, that's not far off the equator line there. Okay. Well, actually, I suppose, it's not too far from North Africa there, look. Okay, which I know is not the equator, but you know what I mean. It's very far south. So this is what causes electrical dysfunctions and planes to be grounded, because it's just too charged, and it will just cut out the planes. It will cut out the electrical system. You get power surges through transformers and stuff like that. I mean, you'll see this as far as France. If you say you're in the UK, you know where France is. You'll see these here. Depending where you are geographically, obviously, if you was going across the Atlantic Ocean there, you'd get brilliant views of the auroras. Okay, brilliant views. So this is the KP9, and these lines here are the magnetic field lines, horizontal magnetic field lines around Earth. Okay, so now if we go to the KP values, which is here, just an illustration, just to give you an idea of what we're talking about when we post. Okay, so you've got KP0, KP1, KP2, and so on, okay? So when it's a KP0, that means the green auroras can only be seen to about this level, all the way across the globe. This is just the UK, Europe, you know, Finland and places like that at the moment. Iceland here, look. So this, say we get, you know, just a very mild solar wind from the sun, like say 450 kilometres a second, which is quite small and quite slow. When that gets pulled in at the pole, they'll still get pulled in at the poles, don't get me wrong, we're always going to have auroras, but it just depends how bright they are. So when it's 0 kp, the green auroras will only be seen in the northern latitudes. It will literally just only go down to this magnetic, these are classes, this is like an interpretation of the horizontal magnetic field lines going across Earth, okay? So they're wrapped around the whole globe, okay? So when it's 0 kp, you will only see the auroras there. When it's at 0, that means that when it comes in and it's kp0, it's disrupting this magnetic field line. That's what gives us that reading of kp0, okay? Same happens when it touches this magnetic field line. That'll give us the kp1 value. And then the green auroras will be seen to that level, okay? Same again. So when you get down to like level 5 kp, which is like a moderate geomagnetic storm, you know we've had a a fairly strong solar wind, like from a coronal hole, which I'll get to. I'll explain the coronal hole in a minute. So that will disrupt this magnetic field line here, and the green auroras will be seen in Scotland and places like that. So do you see what I mean? So when we get KP9, so this is classed as mid latitudes and this is classed as lower latitudes. Okay, so when we get KP9, this magnetic field line is disrupted, and that gives the KP value reading of KP9, and that's where we see the green auroras. We can see it all the way down here. And I mean, we had a few X flares a couple of years ago, Earth facing, and they went way further south than what you're seeing here. Okay, so that's just to give you an idea of what the KP value. And again, if we get a KP9 geomagnetic storm in this area, say it's a localised, it depends where we are on our rotation, of course, but if it was to occur over this section of Earth, as it gets pulled in at the poles, then planes would not be flying here. There'll be a lot of planes that would get grounded here, a lot of electrical disruptions, a lot of phone signal problems, you know, stuff like that. If we was to have an X45 flare from the sun, Earth facing, then the whole electrical system on planet Earth would be ceased. It would never work again. Just so you know, because I mean, we have had a couple of X20 flares, and it did cause a lot of disruption, but X45 is a hell of a lot stronger. And if that was, because our magnetosphere is actually depleting, because as I showed you, the bow shock is always under a lot of heat now, under a lot of cosmic radiation. So that means it depletes the magnetosphere gradually. It just gradually depletes. So the stronger the flare, the weaker our magnetosphere, means the worse it is for the planet, okay? So that hopefully that makes sense, that KP. These are horizontal lines. The stronger the compression, the more south you'll see the northern auroras, okay? And that's what gives us our KP values. Okay, so if I go to a coronal hole, which I'm sure I've got here somewhere, I'm just trying to, you know, so when I do post stuff, I don't know why that's not, there you go. So when I do post stuff, that you get a better understanding. So you can either refer back to this video and watch it through and skip to the coronal hole bit or skip to the KP bit. Just, you know, hopefully it will just help you guys out. Okay. Oh, what have I done there? Okay, here we go. Coronal holes. So what happens is, as the sun rotates, sometimes coronal holes will form. Now this is a huge coronal hole. I mean, these are the standard sizes that we usually see, actually. I mean, you do get some small ones sometimes, but sometimes they're actually huge. Okay, and I'll show you a comparison to how big Earth is compared to the sun in a moment. So what is a coronal hole? So basically, all these little lines that you see here coming off the sun are magnetic field lines, okay? Now, sometimes the magnetic field lines cannot contain the hot gases in the sun, and these coronal holes form, okay? This means that we get a stronger solar wind because the magnetic field lines are not contained. So you get the magnetic field lines stretched far into space, okay? So when Earth facing, obviously the solar wind is a lot stronger. So you get like 750 kilometers per second. And that'll make like a 5 to 6 kp geomagnetic storm. Do you see what I mean? How it all connects? So it all depends on where it is. So if this was facing Earth now, it would have to turn to about here before the solar wind reaches us, okay? So it'd take about 3 days to reach Earth. You get IMF connection from about here. And then once it turns to this position where it is now, you'll have about 2 to 3 days before the impact of the solar wind would hit Earth. Okay? So hopefully that makes sense a little bit. Right, okay. Sunspots. So sunspots and coronal holes are two different things. Okay, sunspots are like the cold spots on the sun that form. So as you can see here, look, they usually come in pairs, okay? So you'll have one sunspot there, and there'll be magnetic equilibrium keeping them sustained. And this is where a plasma filament will form, okay, from each hole, which I'll show you now before I carry on with this one, actually. Okay. Right, this is a plasma filament lift, which I talk about in my post as well. So here would be a sunspot, okay, where this is coming out of here. That would be a sunspot. And here would be another sunspot, a bigger one there. That would be a sunspot. So you'd have positive and negative, and it would be fighting against each other constantly. And sometimes you'll get snapbacks, which cause solar flares. Okay, so solar flares, coronal holes are two different things. So coronal mass ejections that would cause. And if facing, obviously, that's a stronger solar wind. And it can cause X flares and stuff like that, which I'll get to as well. Okay, so let's go back to that picture. I'm hoping this is making sense. It's the first sort of video I've done on this, but I'm just hoping it makes sense for you guys. So here we go. So what you just saw was the plasma filament lift. So that would be formed out of this part and this part, and that would create the plasma arch, okay? So when Earth facing, if they snap back, and hydrogen atoms will just explode into space. And if Earth facing, that will cause a massive compression on our bow shock and magnetosphere and pull all the particles in at the poles and cause KP 8s and 9s. Do you see what I mean? And then you get electrical disruption, core expansion. Because you've got to remember, again, that our magnetic field is created from the core, the iron flow of the core, okay? So when our magnetic field lines are disrupted, our core is also disrupted, and that causes seismic activity. Seismic activity, volcanic activity. It's like core expansion, it's like plasma reactions in a sense, okay? So everything's electromagnetic, and this is like plasma reactions. This is what occurs. So as soon as we get in a compression, we know that within a few days to a couple of weeks, we're going to get some strong seismic activity because the core reacts as magnetic field lines are disrupted. Okay, same as like dolphins and whales. They use the Earth for navigation. They use the magnetic field lines, okay? So when they're disrupted, you see them washing up on beaches and stuff like that. See, it all connects to the same thing. So, okay, get back to it. So what I've done here, I wrote sunspots. Don't worry about the date. It's just an illustration so you get their understanding, okay? So these are like little sunspots that we, you know, they can still cause flares. Look, they're about the same size as Earth. Look, this is to scale. So this is Earth compared to the sun. The sun's 93 million miles away. That's why it seems like it isn't that big, but it is. Okay, so these sunspots are still the same size as Earth, okay? So they can still be quite powerful. Now, when you get sunspots like this, they're like the size of Jupiter. Now, Jupiter compared to Earth is huge. And Jupiter's got it's got the massive magnetic field of its own, which is 10 times the strength of Earth, easy. Okay, and this is little Earth. This is why we're so vulnerable, and why magnetics affect Earth quite easily, because our magnetic field in our solar system is actually not that strong compared to other planets like Jupiter and things like that. Okay, so we will feel the effects of the sun a lot more than the likes of Jupiter. Well, Jupiter's a lot further out anyway, but you get my understanding. Okay, so when these are Earth facing and they snap back, solar flares occur, which I will go back to this just to give you a better understanding. Look, because it does say solar flare here. I know we've gone over this one already. But here, okay, here's the sun. Look, it even says there in the illustration, if it focuses. I don't know why it's not focusing. Hang on, bear with me. Okay, it's not focusing very well, but it says sunspots there. Okay, and look, these little black dots here are classed as sunspots. It's just the illustration, and it's illustrating a solar flare. Okay, and then obviously the solar flare hits our bow shock, like I've gone over before. But when it's like a strong solar flare, like I was just talking about, this would compress our magnetosphere quite far inwards. And then we'll get more poles that get through this shield, okay? More particles get through the shield and then cause a very strong geomagnetic storm, which goes down to the lower latitudes, okay? So the green aurora will be seen at the lower latitudes. And then we get bigger earthquakes, electrical disruption, etc. So hopefully that is making sense. I really hope it is. Okay, right, where are we? Just so you get a better understanding of latitudes, just in case people don't understand what that is either. Let me try and get rid of this. Is that better? That's better. Right, okay. So, imagine the KP values. This is the higher latitudes. So this would be like KP 0, 1 and 2, 3, okay? Mid latitudes is KP 4, 5 and 6, maybe even 7. And the lower latitudes is KP 8 and 9, okay? So that's where you'll see the KP 9 geomagnetic storm conditions, okay? KP 7, 6 and 5 in here, that's where you'll see the green auroras, okay? And then 0, 1, 2, 3, 4, you'll see the green auroras in this section. Do you get what I mean now? Hopefully it makes sense. Okay, let's talk about, again, this is all correlated. So when it comes in at the poles, our magnetogram will fluctuate as well. You see this? This is something to keep an eye on, because, you know, when we do posts, we also put stuff like this in there. So when the particles get pulled in at the poles, the magnetic fields get disrupted, and this is like our, you know, little warning sign here. It's just, look, it's really disrupted. Don't worry about the date again, because I'm just using it as an illustration of what you're looking at, okay? So when it gets pulled in, this is disrupted, and that gives us a little warning that our magnetic field lines are being disrupted, okay? Oh, excuse me. Let me go back. Okay, what should we go to? Okay, this is what, I mean, this is a few days old now, but this is still in January, so this is from the 1st, I think it's from the 1st to the 7th of January. So this is all the earthquakes. This is worldwide. So you can see we're not very far into the month, and look, we've got sixes forming, look, sixes. I mean, there was a lot of six. This was actually a 7.2, got downgraded. So as you can see, the Ring of Fire, this is the Pacific Ring of Fire. Okay, if you follow my cursor, and there is a huge magma plume underneath the Pacific, okay? There's an origination zone here, which is near Fiji. That's where you get some really deep quakes, and there's an origination zone here where the magma arm is. Okay, this is a mid-Atlantic ridge. Look, this is why it's important for the UK, because when that separates, or when this separates, a UK tsunami occurs, and the little one for the east coast of America. Okay, so that's the bit that we have to keep an eye on in the UK, is this section here. And obviously Iceland is a volcanic island, and that sometimes gets a lot of seismicity and volcanicity. Okay, so this is what occurs when we're on our backside alignment, which I wanted to get to. So our backside alignment is what I'm going to show you next, and this is what happens when we're in our backside alignment. These sixes, all within 7 days, okay? because our core is it reacts, like I was just going over. Our core reacts when our magnetic field is disrupted, okay? So I'll go on to, so you see the earthquakes then, didn't you? Okay, this is all because of the continuation of this, okay? Where our magnetic field is really disrupted. That's what's causing it. Look, you see the red coming off the planet, look. See the red lines? You see that? That's strong. That is strong compressions. That is strong magnetic disturbances going on there. And this is all coming on from the southern ecliptic. Okay? It literally hit that and it just whip around everywhere and then goes in there and oh my god. And then obviously because look, these are connected to our core. Okay, these lines here connected to our core. If they're disrupted, the core is disrupted. And that's what causes the earthquake progression. Okay? Which is continuous. So okay, backside alignment we want, don't we? Okay, let's have a look from under the ecliptic. Ignore the date, that's the 9th of Jan. Like I said, I've done this a few days ago, okay? So from under the ecliptic, so this is, you see these lines here? These lines here, these orbital lines? That's the ecliptic plane, okay? They're not obviously all directly in a line. They do like go up and down slightly. Not everything is perfect orbit around the sun. Okay, but that's the ecliptic plane. These lines here, that's the ecliptic plane. And the brown dwarf is just under the ecliptic. And our backside alignment has already occurred here. When Earth was here, where the cursor is now, that's where our backside alignment occurs. Okay? It was like I think it was the 22nd it started, our backside alignment of December. And now, we're still in the backside alignment. We're still in it. Because there's a lot of electromagnetic energy coming from the brown dwarf and then hitting our sun and then coming out and hitting Earth. And then obviously the solar wind comes from under the ecliptic and hits Earth from below. That's when it hits our magnetopause and disrupts our magnetic field lines at the back, the magnetotail. Okay, just so you get a better understanding of what you're looking at from under the ecliptic. Now let's go to above the ecliptic. If it loads, my computer is great. Okay, this is a view from above the ecliptic. Okay, so you get the orbital lines again here. So you got Earth. This is not, by the way, this is not to scale. I've enlarged the planets just so you can get a better view of where everything is. Okay, obviously they wouldn't look like that. They would look tiny in comparison if we was at this height. Okay, so this is the Sun. This is Earth. This is Venus. And this is where the brown dwarf is situated, okay? So when it was the 20, I'm sure it was the 22nd, our backside alignment. And then what happens is the energy transfers from each planet and each star. And then the core expansion occurs, okay? So it sort of charges the core. Because our core is actually a plasma that acts as a solid. So when you're getting plasmatic particles coming in, it literally instantly affects the core, okay? So that's what was occurring. Our backside alignment on the 22nd, that's what was occurring. Our core was just warming up, ready to release, and then it released the 6, and then it started warming again, and then it released another 6, and then it released another 6, and then it released another 6. Do you see what I mean? And now we're coming out of our backside alignment gradually, okay? It's not until we hit February and March. Well, February is our like Goldilocks zone where we're in the clear for a little while and it will start calming down slightly, okay? So you still get some 6s and some 5s, but nowhere near as many 6s in 1 week. Do you see what I mean? Okay, so that's above the ecliptic. Now, where are we? I had another one on here. Oh, yeah, this is what I wanted to show you. Just to give you an idea of what electromagnetic portal connections are. I've drawn these on here. Excuse my artwork. It is obviously fantastic, as you can tell. This is just an illustration of where the system is, the brown dwarf and the 7 orbiting planets. Okay? It's just, it's just a rough sketch, okay? So these are classed as portal connections, okay? This is what keeps every planet orbiting our sun. Our sun is the biggest magnet in our solar system, okay? This is our portal connections to each planet. Just an illustration. You won't see them, but this is just an illustration of how it works. Okay, the whole solar system is rotating this way. Okay, if you follow my cursor, it's all going around that way. Obviously, the further out the planet, the longer the orbit around the sun. Okay, I mean there's comets out there that take 800 years to orbit the planet, to orbit the sun. You know, there's planets out there that take thousands of years to orbit the sun. It's just they don't like telling you things like this. Okay, so again, so when we're on our backside alignment, the energy from here and the energy from here is transferable very quickly. So that's why we get core expansion in our backside alignment, because there's a lot of energy, interplanetary energy occurring, okay? Just so you understand what we mean by backside. So when it's our backside alignment, the Earth is on the other side of the sun. So you've got the Earth, the sun, the system, okay? So when we go to our front side alignment, so you get a better understanding, which is here, I believe. Okay, when we're talking about our front side alignment, obviously I've moved things round now to 2019, 28th of June, okay? So Jupiter would have moved to the left in the orbital path, Saturn would have moved a tiny bit because it's further out, but Jupiter would have moved a bit quicker. So now it looks like it's closer to Jupiter instead of Saturn because Jupiter's moved left, okay? So as you can see, our front side alignment is when it's the sun, Earth, and then the system. That means we're in the middle of it. Do you see what I mean? So this is when we're going to get some strong seismicity and volcanic eruptions and stuff like that. I mean, the energy this side of the sun is extreme. So our front side alignment can last like 2 months. Instead of it being 5 weeks at the back, where we get 2 weeks before the alignment and then 3 weeks after, the front side alignment, which is here, which is illustrating here, the energy around this section here is extreme. So our front side alignment lasts a lot longer than our back side alignment, okay? It's all about energy, second solar winds and stuff like that, okay? So talking of second solar winds, I'll get to that now, just so you get an understanding. Okay, second solar wind. Now, this is, again, my artwork, excuse it, oh my God. So this is the brown dwarf here, just an illustration. It's much further over here, by the way, where my cursor's going. It's much further over here, but I couldn't fit it on. So I've just done it so it's south of the ecliptic, okay? So this is, imagine this is the brown dwarf. This is our sun, right? And this is the solar wind. This is like the second solar wind, which I was going on about earlier. So I've put, look, this is the particles coming in from the second solar wind. Lithium, helium, you know, charged particles, electrons, protons, you know, a lot of particles, a lot of charged particles. They hit our magnetopoles, which I was talking about earlier. Okay, I'll quickly go back to it now, just so you know what I'm talking about. Obviously, this is flip reversed, so I imagine the camera's the opposite side. Okay, so the particles are coming from under the sun. Imagine the brown dwarf is here, where my cursor is. It's coming from under the sun and hitting our magnetopoles, okay? That's what it's hitting. And then they spread around the bow shock and then they spread through the magneto tail, okay? Oh, got the wrong bit, okay? So just picture that. Picture the particles coming in from this side. And then imagine this, just with the camera the opposite side of the Earth, okay? So that's what I'm illustrating. So that's hitting the magnetopoles here, okay? And then going in our magneto tail, causing eddy formations around this section. Earth's in the centre. This is our magnetosphere, okay? I know I keep repeating myself, but I just wanted to, you know, hopefully it just gives you a better understanding. I know I keep going on about it, but... Okay, now, what should we get to next? Okay, let's do the Earth wobble. I know a lot of people struggle with this too, okay? Now, this is our zero tilt. So what we're illustrating here is the northern tilt, okay? The wobble tilt, the axis wobble tilt, okay? And if we look, where are we? Okay. So again, this is from the 8th of January. This is when I saved all these pictures. So it's obviously a bit further ahead now, which will be about over here. Okay, so this is the 8th of January 2019 here, okay? The rest of the lines are different years. So you've got the green, which is 2016. You've got the blue, which is 2017. Okay, and these numbers each correspond the month and the date on the month, okay? Now, what I wanted to point out in this is this section here. See this section here? See how all the lines compress? Look, I'll go a bit closer. See, all the lines, they start getting closer together in this section here. So you imagine where Earth is now on its orbital path. Okay, that's where we are in that, well, about here, sorry, about here. So we're now coming out of our backside alignment, okay, which was around here. And now we're coming out of it. And now, as soon as we lose the connection to the sun, which we won't lose the connection to the sun, but I mean, we're going to come out of the backside alignment, so there's not as much energy. The magnetics then pull it back in, you see, every year, and it always starts a bit further back. You see that? See that? It's gone to there, then it was there. Do you see what I mean? It always compresses here. That means we're magnetically connected to something else. Okay, that's how strong the magnetics is of this brown dwarf. Very strong, very dense and very strong. Okay, that always occurs here. And then we reach February, look. Like I said, the Goldilocks zone. Sun regains polarity, okay? It regains the magnetic strength with Earth. Regains it. Because it's like a 90-degree angle then. The brown dwarf would be situated over here. Okay, imagine this is the solar system with the sun in the middle. I'm gonna have to explain this a bit better, but the brown dwarf would be down here. Okay, and this is the February point where Earth would be. And then our axis tilt wobble starts trying to correct itself, but it can't correct itself fully because when we get around here, it starts compressing again where the brown dwarf is. Okay, starts getting disrupted again. So this is like a different view. So this is looking from a frontal view of the solar system, okay? So Earth's over here, the sun would be in the middle, okay? And the brown dwarf would be over here. But this is just referring to our axis tilt wobble, which is that bit there, look. If I can get over there with this. Sorry, it's hard to do with a phone and computer at the same time. Okay, this is what's illustrated. This is our geographical North Pole, going through here, look. Geographical North Pole. And this is our axis tilt wobble, magnetic, okay? So, how am I going to illustrate this? Let's go back to this. Okay, so imagine looking at it from the opposite angle. So imagine we're looking at it from Saturn. That's the best way to describe that, how you're looking at it. So Earth is here on the graph that I've just shown you. It looks like it's over here. Do you see what I mean? Do you see what I mean? Hopefully you get what I mean. Anyway. Okay, latitude we've done. Oh, we've covered a fair bit here. All right, I'm going to give you a clue of what magnetic reversals actually look like and what happens. Okay, so this is just a normal north and south magnetosphere. Okay, these are magnetic field lines coming off. Okay, magnetic field lines, and that's what gives us our magnetosphere. All from the coils in the core. Okay, now during a reversal, you get lots of north and south poles because the core changes the flow. Okay, so the magnetic fields go absolutely everywhere. So imagine that. Imagine the core changing flow. Imagine the crustal displacement you would get from the reactions occurring within the core, okay? That's what you've got to understand. All this would cause crustal displacement in the lithosphere, tectonic plate movements, earthquakes, volcanoes. You imagine it, that's what we'd get, okay? Tsunamis, it's just, honestly, that's what's going to occur when we have a magnetic reversal. People, you know, there's a lot of people out there that don't understand fully what a magnetic reversal is. A lot of people think it's, you know, it won't hurt the planet, it doesn't do anything, but they always forget that it's connected directly to our core, and our core is what gives us our magnetic field, and that's where all our magma is. And they think that the magnetic field lines are just going to move around on their own without causing any lava upflow whatsoever. No pressure under the plates. That it just means they haven't studied it properly, and they just don't know volcanology very well. Okay, so when people say to you, "Oh, well, magnetic reversal is not going to be as bad as you think," I promise you, they've never researched it all entirely. Okay, they're just thinking that the magnetic can just flip. You know, if you hold a magnet in your hand and you flip it, of course, it causes no problem whatsoever. But when you've got a molten rock core and the magnetic field is created from that, if that is flipped and disrupted in any form, the core will react. And earthquakes will occur, plate movements will occur, volcanic eruptions will occur. Okay? It's all correlated. So hopefully that, what I've just done there, will give you all a slightly better understanding of what I mean, okay? When it comes to charts and stuff. So hopefully you can go back to this video. Oh, what's happened there? You can go back to this video and refer to it and just listen to it again, maybe, okay? I just wanted to touch on this lastly. I know I've gone on a bit, sorry. But, okay. So this is the data for the magnetic North Pole migration, okay? So here is where it was in the year 2000, okay? And now look, it's starting to jump quite far down here. It's sporadically moving. And this is where we are now. Our magnetic North Pole is here now, okay? Now, once we reach this point, so remember, I was talking about the KP index, okay? And how it affects the magnetic horizontal lines, okay? This is what it's classed as. Okay, see these lines here? It's like the horizontal magnetic field lines, okay? In fact, I'll quickly go back to it, just so you can get a better understanding, okay? So what you're seeing is the pole migration. Imagine seeing the pole migration on the magnetic field lines, okay? It's getting weaker and weaker. The magnetic field lines get weaker and weaker the more south you go, the horizontal ones, okay? Obviously, all the magnetic strength is in the north and south poles. So, the closer you get to the equator lines, the weaker the magnetic field lines are, okay? So, if we go back to it, okay, if we go back to it, so the more south this northern magnetic pole gets, if it reaches this 40-degree mark, it's gonna hit the magnetic field lines that are very weak. That means a reversal is imminent. There's nothing that can stop it because the magnetic field lines cannot contain it anymore because the magnetic field lines are too weak. So once we get to hit, remember this is going to speed up now because the magnetic field lines are weaker. So what you're seeing here, the jumps here, this is going to start getting bigger jumps. So it would literally take about 4 years to get to this 40-degree point. And you've got to remember, all the mainstream media are now talking about it. I mean, we've spoke about it for years now. And, you know, a lot of people have started listening. So all I can do is hope that now the mainstream media are talking about it quite aggressively as well, that more and more people are going to start taking notice that this is not a theory. It's not it's a conspiracy. But there's no theory involved. It's all data correlation. Okay? They will tell you that it's just a theory, and they're going to say that because they don't want panic. The last thing they want is panic and an uprising on their hands because they've built their underground dumb cities. They've tried to protect themselves, even though some of them will crumble. They have tried to protect themselves and just leaving the masses to fend for themselves while all this occurs. Okay? So once it reaches this 40-degree point, the magnetic reversal is absolutely imminent. And it will speed up from here over the next 4 years to this point here. Okay? So hopefully that helps. I mean, you can follow all my posts on Patreon. I post on Facebook as well. I always do the same post on Patreon and Facebook. It's totally free. There is a subscription if you want to subscribe to me. It really does help if you do, because then I can do this more often. I'm going to eventually do this full time so I can give more alerts daily and do weekly updates more in depth. Because on Patreon you can structure the posts a lot better. And if some of you haven't seen my Patreon posts, please go on. They're all public, you can all see them, but it's entirely voluntary if you want to donate and become a patron. And I'd really, really appreciate it if you did. It would be fantastic. So I can carry on this work and keep bringing